Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 20th, 2025, about 1 week ago. The standout contribution is a massive, high-fidelity math pre-training corpus that preserves equations and code structure, with two variants at 133.26 billion and 52.32 billion tokens, which drive sizable gains in math and code benchmarks. The paper is titled Nemotron-CC-Math, a 133 billion token scale high-quality math pre-training dataset. And as we will see, the implications for model training are quite significant. Beyond the dataset scale, the pipeline's layout, aware rendering, and LLM cleanup reliably recover scientific structure and deliver consistent performance boosts across math, code, and knowledge tasks. On X, one post highlights the release, stressing preserved equations across MathJax, KaTeX, MathML, and even images, with strong interest shown by likes and replies. Alright, the previous segment highlighted preserved equations across diverse web formats. Figure 1 shows the end-to-end pipeline. It starts from Common Crawl snapshots, filters math-related pages, then renders HTML with links, so layout and symbols survive. A lightweight instruction model cleans and standardizes text into LaTeX, after which quality filtering, deduplication, and decontamination remove noise and leakage. The pie chart at right summarizes topics, with mathematics dominating, followed by computer science and physics. Alright, the previous figure summarized the pipeline and topic mix. Figure 2 shows why normalization matters. The same equation appears as custom LaTeX delimiters, pre-blocks, MathML, and even image tags, which break many extractors. The diagram illustrates the instruction model converting all of these into a single LaTeX format so equations remain faithful and searchable. This standardization is the backbone that preserves math structure at scale. Okay, the previous figure illustrated format normalization. Table 1 compares datasets by openness, document count, token scale, and source domains, which makes the scale difference concrete. Nemotron-CC-Math 4+ lists 45 million documents and 52.32 billion tokens, while FineMath 4+ shows 6.7 million and 9.6 billion. The larger variant, Nemotron-CC-Math 3+, reports 101.15 million documents and 133.26 billion tokens, so it dwarfs MegaMath Web and similar common crawl sets. So the previous table made the dataset scale concrete. Table 3 compares instruction models for cleaning web pages, and it shows that Phi4, despite being only 14 billion parameters, matches or tops much larger models on several tasks. Phi4 leads on math with 40.6 exact match on math and 79.98 on GMS 8K, and it also ties or wins on MBPP. These results suggest the cleaning stage does not require huge models, which lowers cost without sacrificing quality. So, the previous table contrasted instruction models for cleanup. Table 2 reports end results across knowledge, code, and math for models trained on 100 billion and 300 billion tokens, and the Nemotron-CC-Math variants lead most rows. The 4+ set reaches 40.60 on math and 76.27 on GMS 8K at 100 billion, while the 3+ set climbs to 44.20 and 80.06 at 300 billion. These gains indicate effective scaling because longer training consistently boosts math and code accuracy. Wrapping up, two takeaways stand out. Preserving layout and standardizing equations into LaTeX unlock consistent gains in math and code, and the 133 billion token scale delivers stronger results as training length increases. The broader implication is clear. Robust web extraction pipelines can upgrade reasoning without massive model sizes. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.